mathematician David Hilbert urges us to believe in a grand hotel with infinite number of rooms. And these infinite number of rooms all happen to be occupied. I'm guessing some intergalactic Olympic event is taking place or something. A new guest pulls in and he's like, "Yo, I need a room, homie." Not sure why he talks like that. So the manager, the kind-hearted simpleton, cannot turn him down. So he ingeniously comes up with a solution. He asks every guest to move to the room next to theirs. So the dude in room number 1 moves to room number 2, and the madame in room number 2 moves to room number 3, and so on. Since it's an incredibly grand hotel with infinite capacity, albeit full at the moment and at all moments, the manager is still able to make room for the new guests. But then an infinitely long bus pulls over to the grand hotel with infinite number of more guests. The people-pleasing Mr. Can't Say No manager will be like, "Oh, damn." But quickly realizes that it's actually quite simple. So being the kind-hearted genius that he is, he comes up with a new solution. He tells the brand new guest in room number 1 to move to room number 2, the person in room number 2 to room number 4 this time. By moving every guest from room N to 2N, our manager is able to again save the day because now he has all the odd-numbered rooms freed. The hotel is always full, yet always has room. Pun intended. Congratulations, we've just created a contradiction. Infinity is the concept of something that is unlimited, endless, and without bound. The type of infinity our hospitable manager is dealing with is the lowest level of countable infinity, which another German mathematician, Georg Cantor, calls as Aleph Zero. That is just the first smallest level of infinity, the infinity of natural numbers. What? Small infinity? Are there different sizes of infinities? Yeah. There are an infinitely many sizes of infinities. Let's quickly recall some of the different types of numbers that we have for math dumbasses like myself. We have natural numbers denoted by n. This set of numbers is used for counting. These numbers exclude zero and negative numbers to facilitate counting and enumeration or listing. Examples include 1 crow, 2 apples, 7 samurai, 100 years of solitude, and so on. That's how we count. Integers. This set is denoted by z. These numbers include zero and negative numbers also, and these can be listed too. So examples include 0, -1, 5, up to infinity. Rational numbers denoted by q. You can write rational numbers in fraction forms. The word rational is derived from the word ratio, as rational numbers are the ratio of something. For example, 0.5 is a rational number because it can be written as 5/10. Other examples of rational numbers include -1/3, 2/5, 99/100, and so on. In non-fractional forms, they have terminating decimal points. Irrational numbers cannot be written in the form of fractions. In non-fractional forms, these have non-terminating and repeating decimal points. Real numbers. Any number that can be plotted on a number line is a real number. Both rational and irrational numbers constitute the set of real numbers. In non-fractional forms, these have non-terminating, non-repeating decimal points. A set of infinite natural numbers must be less than integers because integers contain at least twice as many numbers because of the negative numbers, right? Nope, they're the same. A set of infinite natural numbers must be more than the set of infinite even numbers, clearly, because even numbers should be half, right? Because they don't have the odd numbers. Nay, they're the same. We've seen that we can list non-fractions, but can we also list fractions? Is there a way to do that? Let's try to list a few rows of fractions. Interestingly, if we try to list these numbers row by row, we will never be able to reach the second row. The first row is infinite. We will go on forever. So the way to list these numbers is to list them diagonally. We start listing from the first diagonal and move on to the second diagonal, and so on and so forth. This way we can list all the fractions. And that's real nice. Let's take the number line and try to list every number which appears on the number line. Should be able to do that, right? It's going to take us an infinite amount of time in order to pull that off. But it gets interesting. What kind of infinite? Let us start simple. Let's begin with 0. It's dead in the middle, good chap, causes zero harm. We're going to take the first decimal number between 0 and 1. Let's take 0.01. Or should we take 0.001? Well, we could go on forever. Where do we stop? No matter how big a number we would come up with, it would still lie somewhere between 0 and 1. Let's look at it in another way. Consider the following decimal numbers within the range of 0 and 1. These numbers are shown in correspondence with natural numbers to facilitate counting. We want to see if we can count all the real numbers, the same way we can count natural numbers. Both of them are infinite, so each element in one should map to one corresponding element in the other, right? So what we're going to do is we are going to create a new number from this list by diagonally selecting numbers. We're going to apply a simple rule to this newly created number, a rule which I just created. We're going to add 1 to every number and switch 9s with 0s. Okay, I appreciate your patience. And are you ready for this? This brand new number that we have created out of an infinite list of decimal numbers between 0 and 1 does not exist on the list of infinite numbers between 0 and 1. It does not exist on the list because of our rule that we applied. The first number is different. It cannot be the second number because the second number is also different. It's not on the list. If we continue to produce more and more numbers, and since it's an infinite list, we can always add the number to the list, right? I mean, it's an infinite list. Yeah, but we can then always create a new number using our rule, and that number won't be on the list. The numbers between 0 and 1 are so infinite, they cannot be listed. What a lame infinite list, to be honest. This is, by the way, what is known as diagonalization, and it was introduced by Georg Cantor, who was laughed at and criticized and called mental for this exceptional discovery. He eventually died in a mental hospital. So, is there a bigger infinity between decimal numbers from 0 to 1 and an infinity between the natural numbers from 0 to infinite? Is there a difference of size between an infinity which is countable and an infinity which is uncountable? Is there a set of numbers bigger than natural numbers but smaller than real numbers? This is known as the continuum hypothesis. It took another remarkably brilliant German mathematician, Kurt Gödel, to finally conclude that we cannot disprove it. And nothing would go wrong in the world of mathematics if we accepted it as true. It took another remarkably brilliant American mathematician, Paul Cohen, and like 2 decades of research to finally conclude that we cannot prove it. And nothing would go wrong in the world of mathematics if we accepted it as false. So our understanding of mathematics is just not comprehensive enough to answer the problem of the continuum hypothesis. The math we know does not know that. We do not know that. And not just that, we cannot know that. So we settle the matter by admitting that none of the known mathematical methods suffice to settle the problem one way or another.